We present LiDeRe, a lightweight readout for fast and data-efficient dense prediction. LiDeRe is an approach for dense prediction, for example, semantic segmentation on small datasets. This is common in many applied computer vision problems where labels are scarce and expensive to get. Our idea is to train only a small parameter readout on top of frozen feature backbones like Dino v2. In contrast to naive linear readouts, which are limited by the low spatial resolution of the backbone features, our predictions are much more fine-grained. Despite the small number of parameters, it achieves a strong performance, especially when fine predictions are required. When combined with LoRa, even better performance is achieved.
Let's start with the underlying idea. Interpolation can be written as a matrix multiplication. Here, X is the flattened image and I is the interpolation matrix. This matrix has two key properties. Its entries are non-negative and its rows sum to 1. This structure resembles the attention matrix of scaled dot product attention used in transformers, which is also non-negative and row normalized through the softmax. In our work, we combine both ideas. Concretely, we generate the interpolation matrix with a small MLP F that takes only coordinates as input. For each pair of source and target positions, we feed their relative distances into F, and it outputs the corresponding entry of the interpolation matrix. Two things to note. The interpolation does not depend on the image content. It is a learned prior, and it only needs to be computed once and can then be cached at inference time. We use flexible-sized queries, meaning we can choose the target resolution independently of the backbone's feature grid. This decouples output size and feature size, so we are not bound to the patch resolution of the backbone. Note, this operation is repeated across multiple heads, analogous to classic attention.
Finally, the full architecture. Features from 3 backbone layers are concatenated. Most of the trainable parameters sit in the linear projections at the input. The feature interpolation module then upsamples by a factor of 2, and a small CNN upscaler brings the output to full resolution. We use a CNN here because of the computational cost of attention at high resolution.
First, we compare against 3 baselines: linear evaluation, DApp, and FETUP. On semantic segmentation, our method combined with LoRa performs best, though by a small margin. For pose estimation and detection, where small structures matter, the difference is much more pronounced. Note in particular the gap compared to linear evaluation. Next, we compare against state-of-the-art PEFT methods for semantic segmentation on small datasets: visual prompt tuning, LoRa, and conv-LoRa. With a VIT-L backbone and LoRa, we outperform all of them while using a fraction of the trainable parameters. Finally, efficiency. Our method is very fast for 3 reasons. No backpropagation through the backbone is needed, unless LoRa is enabled. It is fully compatible with mixed precision, and the interpolation matrix is content agnostic, so it can be cached at inference time. Together, this gives us a multiple times speed-up over methods like conv-LoRa, both in training and inference. LiDeRe is straightforward to use and has minimal Python dependencies. We provide code for both inference, for example contour detection, and training. The example code highlights the efficiency of LiDeRe. Training on just 4 labeled images for around 10 seconds already gives surprisingly good semantic segmentation results. QR codes linking to the paper and source code are shown below. Thank you.